So how many of y'all were at JSConf? Okay, so most of you may or may not have taken the opportunity to see the closing talk in which we announced Tracer, which is a JavaScript to JavaScript compiler written in JavaScript. There are many like it. This one is different. It's different because it's not just only because it's written in JavaScript, but because the source language that it consumes is some variant of what we hope will be a set of features that are in the next version of JavaScript. It's JavaScript of the future, more or less, to JavaScript of today, strictly speaking, ES5. So browsers that run ES5 or environments that run ES5 like Node can take advantage of this. And so all the demos we did for JSConf demoed Tracer in the browser, but Tracer absolutely works on Node. In fact, we have a batch mode that relies on Node, uses V8 to go and automatically generate code for you. So you can run it to batch content that you'd like to serve to the client, written in the future version, or you can run it online inside of Node to make it go. But today's talk is sort of not just about what it is and what it does for you, but rather we want to sort of peel back the layers a little bit and show you kind of how it works. Because fundamentally, Tracer is not about like, hey, look, everybody, here's a great tool for you to use. It's a tool that's got an expiration date on it. And that expiration date is when the language gets much more awesome, you won't need it, right? Because you're working in Node on the server, your environment's moving a lot faster than the client-side environment is. You get to choose your version of V8, right? You get to choose your version of the language, and as soon as V8 gets stuff, or as soon as you decide to change your deployment environment, you get all of the advantages of everything you've just dumped into your world, which you don't get on the client side. You're at the mercy of whatever your users happen to have deployed, and they're going to move relatively slowly compared to your server-side environment, which is why I think there's this large and growing population of alternative languages for server-side development, including JavaScript, thank goodness. So because the economics and the constraints of the client side are different than the server side, we can use that to help move faster on the server. And so this is the community that's going to be able to try out this new stuff faster, use it first, stretch its legs, and provide this sort of detailed feedback we absolutely need to make sure that the next version of language has all of the right stuff in it and none of the stuff that we think is buggy. So Harmony is pretty awesome. So the stuff that's already on the slated for the proposals list for Harmony gives us modules. It gives us proxies. Proxies are amazing. If you've used Node Proxy, you've seen it firsthand. Or proxies under SpiderMonkey. Harmony gives us a bunch of syntactic fixes. It gives us semantic fixes for things like asynchronous module loading or apparently synchronous module loading with asynchronous behavior. The sorts of stuff that you wind up doing all the time in either Node directly or in patterns that you sort of carry around with you in code that you're working on. So for example, the Node has its own require system, which is synchronous, right? Which is sort of mirrors the apparently synchronous behavior of what's happening under the covers in Harmony modules. And so we sort of see this pressure being taken off of patterns and off of libraries by the language when we move to Harmony features. And so I just want to give you a really simple example, and sort of we're going to walk through what happens inside of a compiler from point A to point B when we go from source language to the destination target. Because what we really want out of these compilers is for them to hopefully be backwards compatible semantically. Like we want the next evolution of the language to be built on primitives that we know and love, right? For instance, when we go and talk about classes, we don't necessarily want class-based OO fused into the language in a way that's sort of upsetting to the prototypal OO and object composition styles of inheritance that we know and love today. Some people do want that, but they tend not to be JavaScript programmers already. They tend to be coming from a different place. Those of us who love JavaScript, I think, are much more in tune with the idea of keeping prototypal inheritance and giving it significantly better syntax. So that idea of sort of taking the semantic we have, giving it a better way to say what you mean is exactly what we want to get to, I think, broadly speaking. And I know that the committee is working hard to make that happen in a bunch of places. So let's walk through how one of those features that does exactly this, that's got a great expression in today's semantics, can be implemented through a compiler. So this is a pretty common example of a variable arguments function, variable arity function, where you'd have to go denote that in some other piece of metadata, like a JS comment someplace, to note that this thing is going to take more than one argument, which is the actual function.length result here. And it's going to provide a default value for format, which you'd also have to go document someplace else. It's not actually readable in your code. And you're going to have to deal with this parameter thing because, arguments isn't actually an array. Things are messy. OK, so Harmony gives us a much better answer. Harmony lets us say, I'm going to provide a default parameter value. So if I don't provide one, it's going to be defaulted to that empty string. And everything else that you pass in beyond the initial is going to be bucketed into a local variable called params. Right? That's pretty awesome. That means that no longer are you going to have to shuttling the arguments object around to try and go pull stuff out and try not to mutate it because it's live. Instead, you're going to have an object that does what you want and gives you this really nice terse syntax which has a mirror on the spread operator so that when you go to use it in other places, you no longer have to use call and apply. This is really nice stuff. OK, so how do we get there? Well, let's take this code. So this is what we start with, and this is what we'd like to be writing. So let's take this code and sort of run it through Tracer. So we've got the Tracer REPL over here, and what we've got now is when we type this in, we've got the compiler. Oh, right, you can't see everything. Let's fix that. OK, so when you run this through the Tracer REPL, what you get out of the other side is sort of the exact same thing, except the function has been rewritten for you, right? So the rest of this talk is about how the heck does that happen, right? Because a lot of us sort of treat compilers like they're some big black box. They're a scary thing. There are things that compiler people do, and we're not compiler people. We write applications, but compilers don't have to be scary. They don't have to be somebody else's bag. They're things that we can address. So, yeah. Again, we can see exactly what's going on there. And I'm going to, so I'm going to hand it over to Peter to sort of walk us through the rest of the compiler lifecycle. But if you take anything away from today's talk, I hope that you start to believe that JavaScript programmers can participate in the process of evolving the language, not just by telling us what you want or telling us what you need, by helping us prototype this stuff, and we'll show you how.
Howdy. Hey, I'm Peter Hallam. Thanks, Alex. So I'm a compiler guy. I'm just going to try and walk you guys through sort of the basics of the anatomy of a compiler. And basically, at a high level, a compiler is just going to take a source program that you've written and convert it into something else. Some compilers you'll convert it down to machine code, and this compiler is going to take source code that which is JavaScript plus new features and turn it into JavaScript of today. Compilers is a pretty well studied domain, and so there's some common patterns that you use to sort of get yourself through a compiler. So the first stage of a compiler is called Lexing, also known as scanning or tokenizing. And basically what you do is you take your source code as an array of characters, and you turn it into an array of tokens. Once you've got an array of tokens, you do the syntactic analysis. So you parse the tokens and turn it into a tree. I'll get into a little bit more detail of what this looks like. Once you've got a tree that represents your program, then you can transform that tree from a tree containing so each statement each node in the tree is going to represent a statement in your program. And so a transformer will take nodes that are not representable in the output language and transform them into nodes that are representable in the output language. And then lastly, once you've got a transform tree, then you just write that tree out and convert it back into characters again. And I'll just walk you through that pretty quickly here. So the first thing is Lexing. And as I mentioned, Lexing is the process of basically just taking characters and turning them into tokens. And here's a code snippet from Tracer that shows you basically the basics of Lexing or scanning a token. We start by skipping comments. We remember the index of the beginning of the token. If we're at the end of the file, we just create a token which is the end of the file. Otherwise, we grab the next character, we look at it. If it's an open curly, we create a token which is an open curly, and we note the beginning of the token. And so the create token does pretty much what you'd expect. It creates a new object, which is a token. It stashes the token type in it, and it stashes the location. And if you've got more information, like the token is like a string or a number, it's going to store the string or number value into the token object. But really, at the end of the day, this is the sort of the core of what a tokenizer does. Obviously, there's a bunch of stuff scaffolding to kind of get you to set this up. But at the end of the day, it's really tokenization is pretty straightforward. So once you've got your tokens, then the question is, how do you build a tree that represents your program? So you want to have like one node, say, which is a function, and the children of the function are going to be, the arguments of the function, the name of the function, the body of the function. Well, first thing you do is you get your token stream, and you ask yourself, hey, what's the next token in my token stream? If it's a var, then you parse the variable statement. If it's a function, you parse the function declaration. And of course, obviously, there's a whole bunch of other options in here. But at the end of the day, this is sort of the basics of it. A lot of folks, come out of college, and in college they tell you, hey, you got to use a parser generator for this. It turns out that most of the guys I know that have been doing compilers for a long, long time actually don't use parser generators. And there's a bunch of reasons for that. The first reason, basically, it comes down to the fact that, writing it hand-coded yourself is actually really not that hard once you understand the patterns. It kind of also uses one of the arguments that I think folks are using for Node.js, which is there's value add in having just one language in your system. If you use a parser generator, you express your grammar in a language which is not your programming language. And there's a lot of value in having just one language in your system. It makes it much easier to debug. Anyways, there's a bunch of other reasons that I won't get into in terms of why I think parser generators are perhaps not the best tool. So again, what happens when you want to say parse a function? Well, again, it's a similar kind of thing. There's not a lot of magic to it. You stash away the location of the start of the parse tree so you can give good error messages. You eat a function token. You check to see if there's an identifier, which is the name of the function. You eat a paren. You eat your formal parameters, your close paren, your function body, and then you create up a new object, which is basically just got all these values as members, and off you go. So again, there's not a whole lot of magic to this. I'll just give you one more quick example. An if statement, again, looks very, very similar. This is code that I just cut and paste from the compiler. You walk through, you just eat the tokens, the token types that you're expecting. The only tricky bit here is that, we're peeking for the token to see if there's an else clause or not. And then we build a new node which represents the if statement. So again, not a whole lot of magic here. And once you recognize the patterns here, it's actually pretty readable, and it's actually not too bad compared to, say, a BNF grammar. And again, the nice thing about this is you don't have to learn a new language to express to express the grammar of your language. So transformers. Transformers are where the real work is done. This is where you're taking a tree, the parse tree, which represents your program, and transforming it into a subset of the language which does not include the features that are not in sort of JavaScript now. And this is one where I'm gonna just switch to VI here quickly. Hello. So this is the transformer for REST parameters, and basically what it is once you walk your tree, and everywhere that you find a function with a REST parameter in it, you basically call this function and you do this transform, that's described here in the comment. A function with a rest parameter here, and it gets turned into a function that looks like this. And you can just kind of walk it backwards. We're creating a function declaration. It's got the same name as the input function. We've transformed the parameters without rest, and you can sort of see that happening sort of up here. And of course, we transform the body by adding a block to, or adding the extra variable statement, which has the call to array.prototype slice. And again, it's a little bit, reading code that's building up trees is kind of gnarly. But again, this is, there's not a lot of magic here, and once you understand the patterns, it's something that you can actually read. All right. And then lastly, output. So once you've transformed your trees, you've got a tree that represents sort of the output that you want. You just turn that output into text. And we've got some simple primitives here, where you just say write. So for a function declaration, you write the keyword function, which is just going to write, the text function. If it's got a name, then we write the name. We write an open paren. We visit the formal parameter list, close paren, function body. Again, it's a pretty straightforward system once you look at it. Now, of course, the trick to all this is sort of knowing the patterns and setting up the patterns so that you can actually compose this well. But once you've got that, then the actual meat of it is actually fairly straightforward. Now we. All right. So I want to walk you through a little more sophisticated transformation, which is the async function, or it's called deferred functions rather, which is a language feature that we're looking at to try and help with asynchronous callback style programming. And I went through this a little bit in the talk at JSConf, and I want to kind of go into a little bit more detail, sort of how the transformation works and so why this is and I think at least is helpful to you. And so here's a piece of callback code. We've got an animate function. It takes an element, an HTML element. This is a browser scenario, obviously, and it takes a callback to say, hey, once this animation is finished, call this callback. And what's actually happening here is we're just setting the style of the left margin of the element and in a loop, and then each time through the loop we wait for 5 milliseconds until we get to the left margin of 350, and then once we're done, we want to invoke the callback. And so, if for folks that are familiar with callback programming, this is perhaps relatively straightforward to read, but it's anyways, it's pretty interesting. It does twist up the code quite a bit. And then, so we want to, and in our example, we're going to animate this element, and then we're going to, when we're done, we're just going to have an alert that says, hey, okay, we're done. I know there's browser libraries. There's this deferred pattern, also known as the promise pattern. And the promise pattern allows you to compose functions that, asynchronous functions, a little bit better, because by moving the callback out of the argument list and returning an object upon which you can add a callback. This is, again, code is just all ECMAScript now, so there's no new features here. But here we've got a defer timeout, which returns a deferred object, creates a deferred object, calls Windows set timeout. And when the timeout happens, it's going to signal the deferred object and say, hey, you're done now. So call all the people, and then it's just going to return that object. And the animate is every time it wants to actually wait for 5 milliseconds, it's going to basically call defer timeout with 5 milliseconds, and then it's going to say, when you're done, add my continuation, add my callback to the return value. And at the same time, this animate function is also going to return a deferred, and when it's done, it's going to just say, hey, I'm going to signal my deferred that I'm done, and so the caller of animate now doesn't pass in the callback. It just adds its continuation onto the return value of the animate function. So so this is kind of nice because you can just say, animate. It reads kind of nice, right? It says I want to animate something and then I want to do an alert. All right, so it reads a little bit more composably. Unfortunately, when you start getting into for just straight linear composition, I want to do this, then I want to do this, then I want to do this. The then composition works quite well, but here, what we're actually have is essentially something very much like a for loop, but it's actually unrolled, and to turn it into a callback. And there's, I'm a compiler guy, and so I speak compiler, and there's a transformation. There's a description of this transformation, and it's called continuation passing style, and it's actually a very well understood transformation in the compiler community, and it turns out that a lot of times when you do this transformation, when you're doing these transformations in compilers, you actually use this continuation passing style technique and have it actually automated by the compiler. In the opening talk, it was mentioned, what is some of the biggest problems with Node? Well, one of the biggest problems with Node is that you have to turn your code inside out using continuation passing style, right, using callbacks, and that's something that is a real barrier to entry for folks in Node. And so the question is, well, if compilers can do this CPS for you, what can we do to make this easier for you, more readable? And so what I'm going to show you, and so this is where, now this is the same, everything we see here is the same function. So the defer timeout is exactly the same code. The way that animate is chained on is exactly the same. But now you'll notice that the animate function is using sort of this proposed feature here, which is called await. And what is happening here is when you any function that contains an await, when you see a await of an expression, it says evaluate that expression, and then attach the continuation of the function I'm currently in to the end of that deferred object. And then what I'm going to do is I'm going to return a new deferred object to my caller. So semantically, this is doing exactly what was happening in this previous slide, all right? But instead of having to turn this into continuation passing style with a callback, we can just write it like a regular for loop. And the hope is that with this kind of language feature, we'll actually sort of takes a lot of the difficulty and of sort of coming to the callback style world out of Node. All right. So much for transforms. So I'll show you what this is going to end up looking like. Hang on. Just pop it into the REPL loop. And what I'm going to do is I'm just going to get rid of this so that it shortens up. Okay. So this is actually showing the generated code that the compiler is going to generate for you for this. So here's our defer timeout, which we just kind of commented out, and here's the animate function. And what happens is the compiler turns your function into a state machine, and basically every line, every statement in the input basically gets turned into a single state in our state machine. And then the compiler sort of knits the state machines together by and hooks it all up. So so for example, our first state here is left equals 0. Then we've got left less than 350, and then we've got element style, and then we've got their await. So let's walk it through, and you can see here's our left equals 0. Then go to state 6, and then state 6 says do the comparison. Based on the comparison, we decide to go which state we're going to go to next. So again, there's no magic here, and this is obviously not as pretty as the CPS transform code that you would write yourself. But the nice part about this is that you didn't have to write this at all. The compiler wrote it for you. Anyway, so and then I'll just take you through the actual meat of this. Here we're actually saying, hey, call defer timeout, and we're going to get a wait task back, get a variable back. We're going to attach a callback and an error back to onto that object, and then we're going to return back to our caller. And if the callback is called, we're going to go to state 1. If the error back is called, we're going to go to state 2. The nice part about this is that it actually chains all your exceptions as well. Question? You're asking about this code here? Yeah. So there's dead code in here, and the reason why is just that the way that this code is written is we focused on trying to make the transform simple as possible and understandable as possible, like the transforming code, I should say, the code that's generating this, as opposed to trying to generate completely optimal output. The actual transformer code. Okay, so I can show you the transforming code. Let me do that. What is it? Async. Good Lord, where is it? Hang on. Sorry.
So I think the important part to remember here is when you're looking at what's happening here in the transformation, it's sort of like this library of hacks that you put together to sort of achieve something in JavaScript, right? Where JavaScript has this semantic available for you, and you just have to put together this large pile of code to sort of make it happen in JavaScript. And when you're doing that, that's the exact same library of hacks that you sort of embed into this transformation form of your compiler. You write it a different way, but if there's something that you want to achieve through syntax in JavaScript, once you sort of walk through this set of steps in the compiler chain, the end state for each one of those hacks that you're giving syntax to is this transformation. It's exactly the same code that you were going to have to generate yourself or write out longhand yourself. And the front of the compiler toolchain is just there to get you into a state where you can transform this tree to generate that same thing that you were going to write by hand. So if you think about it in terms of like, I'm doing this a lot, I write it all the time, I want to stop writing it all the time, and then walk back from there, it's really easy in many ways to start, especially if it's all JavaScript, especially if it's all one language, it's really easy to start hacking on this and say, it'd be great if JavaScript did this instead, and makes it really straightforward to start working on it. This is the worst case scenario. So if it doesn't scare the heck out of you, you too can work on a compiler.
Yeah. So this is actually like by far the gnarliest of the transforms. So anyhow, so this is and the trick is just to sort of break it down into cases and roll it in.
Yes.
Are we out of time? Okay. And that's basically it. If you're interested in looking at the tracer compiler, here's the links. Yeah, thanks for your time.